Share. I'll share screen. Okay. Okay. So sorry for the delay, everybody. So I'm gonna. I thought I would kind of wax a bit philosophical today to make it more enjoyable for the audience. So there are some kind of technical things that I'll get to about some recent research, which is well. So initially, it's some work with okay, so it's some work with Joe Harrow, who's my student, he submitted before Christmas, and his thesis is very big, and this is just a small part of the thesis. Actually, it's the first thing that we published together. So that's some work about Somos sequences and integrable systems over the dual numbers. So I'll explain what that is in a minute. And then with various other people, so Sasha Mikhailov and Paul van Hacker. So Sasha Mikhailov is in Leeds, and Paul is in Poitiers, and then Jinping, who you all know, who's now in Wang, so who's now in Ningbo. So I oh, that I convert her Jinping Wing. Yeah, there we are. So let me get it right. Well, I'll show you Jinping in a minute. So so the thing is that yeah, so Jinping just moved to Ningbo recently, but actually it's kind of relevant to what I'm going to talk about. So I'm going to talk about I'm going to just talk about non-commutativity for a while to sort of ease into the topic. But in September, there was a group in Ningbo organized this conference about Poisson structures and non-abelian integrable systems. So non-abelian is just another word for non-commutative. So that was the main topic of the meeting. So it's quite a kind of current topic at the moment, is to look at dynamical systems over non-commutative algebras, basically. So that's kind of broadly speaking, that's what I'm going to talk about today. But just to show you the riverside, the old Bund in Ningbo. So there's Jinping, and that's Pavlos Zenatidis, who's another former colleague from Kent. And that's Sasha Mikhailov, and then Sasha Veloslov, and Sotiris, he's based in Yaroslavl, actually, in Russia. But anyway, so these were some of the people from the meeting, and I would, yeah. So Ningbo is actually older than Shanghai. So that, if you know the Shanghai skyline, that part is quite similar to Shanghai, but it's actually sort of several decades older, so people settled in Ningbo before Shanghai, and that's there's a kind of river area also in the old town in the middle, which is very pretty as well. So anyway, that's just to set you the scene for non-commutative integral systems. Is that if you're going to go to Ningbo, it's a good place, and there's a very good group of people working on integral systems. Okay, but what I said is I'll tell you a bit about non-commutativity. So that's sort of my first sort of topic, is to say something about non-commutativity. So why are we interested in non-commutativity? So normally when you deal with variables, so that could be in dynamics or in in geometry, then coordinates variables, they're commuting. But then there are lots of cases where non-commutativity arises. So, of course, when you do algebra and you study groups, then most groups are not abelian. And one of the sort of simplest examples is if you take rotations in three-dimensional space, so around a origin, so that's the group called SO3, so it's the special orthogonal group in 3 dimensions, and generic pairs of rotations in 3 dimensions don't commute. So for example, if you do a rotation around the x-axis and then do a rotation around the y-axis in x, y, z axes in 3D, and then you do them in the opposite order, then you get a different result. So that's an important sort of example in geometry and group theory, if you like. And then another important example in physics. So I don't know what that is. Another important example is in quantum mechanics. So I'll do this. And operators don't commute. Okay, so what does that mean? Well, for example, if you have just a single particle in one direction, then the position operator, I'll call that Q, and the momentum operator, I'll call that P. Momentum is P. And then if you work out QP minus PQ, which is called the commutator, so that's written normally with square brackets, then that's not equal to 0, it's equal to I times Planck's constant divided by 2 pi. And I guess there's an identity operator there if you want as well. So if we could put a 1 there to mean the identity operator, so that's called the Heisenberg commutation relation. So there are lots of places in maths and physics where non-commutativity is important. And so if you go beyond classical mechanics, which is what I'm going to start off, I'm going to say a bit more about classical mechanics in a minute, then when you move to quantum mechanics, you already have to deal with non-commutativity, and how you actually go from a classical system to a quantum one or quantize it is a rather sort of delicate procedure, and there isn't a sort of general recipe to do it, and it's something that particularly Jingping and some of her collaborators have been working on a lot recently. Okay, and then another reason to think about these things. I mean, why in physics you have lots of groups, so lots of types of symmetry that arise. So I just thought I'd mention some things about groups and symmetry and non-commutativity. So if in particle physics you have the basic forces of nature. You don't, in particle physics, you don't deal with gravity, but in electromagnetism, there's a symmetry which is U1, so that's just the unitary 1 by 1 matrices. So that's just all of the complex numbers of modulus 1. So that's the symmetry in electromagnetism, which is the same as the rotations in the plane or the symmetries of the circle. So that's the symmetry in electromagnetism. And then the weak force, you have SU2, which is the 2x2 matrices, which 2x2 unitary matrices with determinant 1. And then the symmetry of the strong force is SU3, which is the 3x3 unitary matrices with determinant 1. And so electromagnetism is an abelian symmetry, the rotations of the plane, abelian. It doesn't matter about the order, but these other two symmetries are non-abelian. So those are the symmetries that you get there. And yeah, just for people that don't know what these notation means, we're talking about unitary matrices. Means that you have a matrix U, and if you multiply it by its Hermitian conjugate, which is the complex conjugate transpose matrix, then that's the inverse matrix. So U DAG equals 1. So all of these groups consist of matrices of size 1, 2, and 3, which satisfy this condition. And then the S, letter S means special. So that means that also the determinant has to be 1. So that's what those are symmetry. So in physics, there's symmetry. But then coming on to the reason that I'm talking about symmetry. So these symmetries are kind of well established in particle physics. But then there's other kind of symmetries that you can have in physics. And not all of them are well established. So these are things that are part of what's called the standard model of particle physics, and in all the particle accelerators, like in CERN, there are very accurate measurements that show these symmetries appearing in the interactions of particles. But there's other kinds of symmetries that would sort of be nice, and one such symmetry is supersymmetry. So now I'll tell you about another kind of symmetry, which is supersymmetry. Okay, so sorry, I didn't do this in the right.
And you can actually ask the question.
Yes, of course.
Okay, so
yeah. Yes. 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 Yes.
Is there an understanding of what deformation quantization means in physics? Is that
Yeah, but okay, I'll come on to that. I wasn't gonna start with that, but I will come on to that. But the deformation quantization actually comes from the Poisson algebra. So that there wasn't Poisson in my title, but there was Poisson in the title of the meeting in Ningbo. So the point is that when you go from the right deformation is that the H bar tends to 0 is what's called the semi-classical limit. And then what you recover there directly is not the commutativity in the algebra, but actually the Poisson bracket relation in the Poisson algebra. So I'll explain what that is in a minute. But I mean the meaning in a sense is that when in situations where the size of H bar doesn't matter, then things look commutative, if you like. So you only see H bar. H bar is 10 to the minus 34 joule seconds. It's a very, very small number. So you only see it on a very small scale. And so there are situations where in microscope, well, mainly in subatomic realm is where you notice H bar, but then now people have got more and more precision measurements that they can actually see, quantum behavior at larger scale with molecules and even larger sort of extended objects, but generally, because h bar is very small, so the world looks non-commutative on a very small scale, and on a large scale not. Yeah, okay, but I'll say something about deformation from Poisson algebra, but yeah, it's a big topic, but actually, yeah. So I mean, when I come on to it, I'll say some more. Okay, so what I wanted to say just a little bit about is another kind of symmetry, which is called supersymmetry. And that's sort of going to be relevant to the stuff that we did with Joe, actually. Okay, so what's supersymmetry? Well, in the particles that we observe, there are two kinds of particles, essentially two main kinds of particles that all kind of matter fits into. And the boson, there's the bosons, which are the in particle physics, those are the force-carrying particles. So you can just call them the force particles. So if we go electromagnetism, there's one boson, which is the photon. That's often given by the letter gamma. And then the weak force, there's the W and Z bosons. And then the strong force, there's the gluons, which is often just called the letter G of some sort. So those are the three kinds of bosons, and the number of them corresponds to the dimension of the Lie group. So U1 is a one-dimensional group. There's only one boson for electromagnetism. SU2 is a three-dimensional group. There are three bosons for the weak force. And then SU3 is an eight-dimensional group. There are 8 types of gluon in QCD. So that's the sort of numerology of those things. And the point about bosons is that when you look at bosons in a particular state, in a particular state, then they're very sort of happy to multiply and have more and more bosons in the same kind of state. So if we just look at a particular state, and then this is a Dirac notation. This would be called the ground state or the vacuum. So that means there's no particles in that particular state, but that's still a vector in some Hilbert space, some infinite dimensional vector space in general. And then what you do is you apply what's called a creation operator. Actually, maybe okay. Well, I'm going to draw just a few of them. I'll do 1, 2, 3. So these are meant to be kind of funny bracket things, and then maybe I'll use a different color for the creation and annihilation. So then you have some operators, some other kind of operators that act on the states, and what they do is they create a quantum in the particular state. So for this state, well, there's a creation operator which is a dagger. And then if you apply a dagger to the vacuum state, then it gives you it creates one quantum in that state. And then you can keep on applying a dagger, and you can go on applying it as many times as you like. So you just go on, and you get an infinite tower of states. And this is called a single boson Fock space. So that's the sort of terminology. But then so the a dagger is the creation operator. But then there's also annihilation operator, which destroys quanta. So you can go backwards. So the annihilation is A, and that's the Hermitian conjugate of a dagger, the Hermitian conjugate of each other. So each time you apply A, then you destroy a quantum. And then eventually, when you get to the ground state, if you apply A, you annihilate completely. So then you get 0, which is really the 0 vector in your vector space. So that's how bosons work. Now, the other kind of particle, though, is the fermions. And those are the matter particles like electrons and quarks and so forth. And those are called fermions, and they have quite a different sort of behavior statistically. So one of the things about fermions is you have what's called the Pauli exclusion principle, and that means that you can't have more than one fermion in the same state. So what that means in terms of this vector space of states, if we just look at a single particle state, then again we have the ground state, and we have one quantum in that state is a sort of excited state, but then there's nothing else. So what does that mean in terms of our operators? If I go back to the operators, then it means that there's a creation operator as before, but now if you are trying to create another quantum in this state, then you'll end up with really zero, the zero vector. And then annihilation, well, annihilation goes back this way. So if you've got an excited fermion state, if you like, then the annihilation operator takes you back to the ground state. But if you apply it twice, then you really get back to nothing. You destroy the state completely. So the point is that the algebra of these operators is such that they're nilpotent. If you square them, you get so the fermion operators are nilpotent. So nilpotent operators. So that's not true for the bosons. So A squared is 0, and A dagger squared is 0 as well. So that's okay. So those are nilpotent. So the thing is that there's a whole algebra, if you like, associated with fermions, and it usually involves sort of quite interesting, well, possibly nilpotent operators, and also some idempotent operators like Pauli matrices and gamma matrices, if you know what those, if you've studied the Dirac equation and so on. But anyway, so the point is that in dealing with fermions, you end up with dealing with these algebra of things which are nilpotent, and there's sort of there's a nice way to think about this just purely algebraically. So what I should say is supersymmetry is an idea that actually there's a symmetry between bosons and fermions, and so that every boson should have a fermionic superpartner, and vice versa, every fermion should have a bosonic superpartner. And so far nobody's found any of these supersymmetric particles, and one of the things is that the masses of the superpartners generally have to be much bigger than the typical masses that you observe in particle accelerators, which would mean you'd have need a huge amount of energy to see them. But nevertheless, yeah, people, well, at least especially in string theory and quantum field theory, people like supersymmetry because it makes a lot of complicated calculations cancel out and become very, very simple. So it would be very nice if it was true, but there's not really any evidence for it being true, I would say. But anyway, on an algebraic level, you need these nilpotent operators if you want to talk about fermions. And so one of the basic things in supersymmetry is what's called, you use what's called Grassmann algebra. So yeah, if I just shorten it, normally it's called SUSY, is the nice notation for supersymmetry. So the n equals 1 supersymmetry algebra is you just have two nilpotent generators, if you like, beyond your ordinary nilpotent generators. Yeah. So for some reason, I don't know, they're often called theta 1 and theta 2, and then they're also often referred to as Grassmann numbers. So when you deal with fermions, then in addition to ordinary numbers, sort of real numbers or complex numbers, you often extend your number system by adding in a couple of nilpotent things, and they satisfy this, what's called an anti-commutation relation. So instead of taking the difference of the two things, which is called the commutator in an algebra, you take the sum of the two things in the opposite order, and then you get zero. So in particular, you get θ1 squared is 0, θ2 squared is 0, and also they anti-commute if you change the order. So that's part of actually fermions when you deal with fermion states, that when you have more different states, then the creation and annihilation operators have to anti-commute when you create fermion states and so on. So that's sort of, but anyway, the point is you need these operators even just in ordinary quantum field theory when you deal with fermions and things. So then your algebra, you can take your algebra to be, you could take like sort of, I don't know, let's say x0 plus x1 θ1 plus x2 θ2. So now we've extended the algebra. We've got the ordinary, you can just think of x's as real numbers, real coefficients in this algebra. But then also, if we take θ1 times θ2, that's also another independent generator in the another, well, it's not a generator, but it's another linearly independent element of the algebra. So you have a four-dimensional algebra now, and these x0, x2, all these coefficients, we could take them to be real, and then more generally, I'll sort of think about them being complex as well, because for other reasons I like everything to be complex. But anyway, so this is the basic supersymmetry algebra, what's called n=1 supersymmetry, and you can split it up into even and odd parts, which is the so like a even. So as a vector space, it's a sum of the odd part is the combinations of θ1 and θ2, and then a even, we can think of that as x0 plus x3 θ1 θ2, and now the point is that this algebra on its own, so this algebra is non-commutative overall, the whole algebra. But if we look at this subalgebra, then this even subalgebra, this is what's called the dual numbers. And now I've forgotten whether it was Clifford who invented the dual numbers, or whether it was Cayley, or it was, anyway, it was one of those 19th century English algebraists, but I think it was Cayley actually. So what are the dual numbers? Well, if you just call this θ1 and θ2, call it epsilon, then we can think of this as like pairs of real numbers. So if we call this θ1, θ2, because if you use that anti-commutation relation, you can check that θ1, θ2, when you square it, also gives you 0. So that's an easy calculation. So now you have pairs of real numbers, if you like, as coefficients, and then you have this generator, which is nilpotent. So this is a bit like the complex numbers, except instead of having something which squares to -1, you have something which squares to 0. And dual numbers are quite interesting objects because they, well, you can use them for various things. And for example, for automatic differentiation. So if you have a function, let's say an analytic function, and then you substitute in dual numbers, then Taylor expansion is very easy because it's just f of x plus y times f dash of x times epsilon. So the point is that you can, if you think about expanding a function and then you just throw in this generator, then you can compute, compute the derivative kind of automatically, especially with polynomials. So actually, even in algebraic geometry, people use the dual numbers to define the tangent space. If you work over a general field, something like a finite field, then you can't really define the derivative as a limit. However, you can define the derivative over a finite field if you extend with the dual numbers. So I think it's maybe something like, I remember it's Hartshorne actually defines the derivative in, for algebraic in tangent space of algebraic varieties using dual numbers, but also in kind of computer algebra as well. So, yeah. Yeah. Clifford algebras is a more general thing. I won't. Yeah, but I mean, inside you can easily embed nilpotent elements inside a Clifford algebra. So a Clifford algebra, you have sort of typically idempotent things. So you have a metric, and then you have things which generators which square to the, if you say you diagonalize the metric, so in a product, and then you have things which square to the so if you have, for example, a non-definite metric, then you can easily get, like Minkowski space, for example, you have null vectors, which are the things which square length 0. So yeah, you can easily embed dual numbers inside Clifford algebras or Grassmann numbers as well, more generally. Yeah.
Is there a special case when theta 1 0?
Well, I'm really thinking if theta 1, theta 2 is a generator in the algebra. So it's like I. You can't just set I to be 0 in the complex numbers, if you see what I mean. It's like there's just another generator in your algebra, which is this nilpotent thing. So you can't get rid of it once it's there.
Essentially, it's not 0.
Yeah. It's essential that it's non-zero. So I mean, it's a two-dimensional extension of the real numbers, but it's just that the complex numbers that you can think of as a two-dimensional extension of the real numbers, except that you have this other thing which squares to -1, and this is just a different extension.
Going from Jordan theory, it looks like 0 there. It's like the Jordan problem being 0, so you think of it as sort of like generated by two elements. Here, so you get a spin algebra, some spin system.
Yeah. I mean, you can fit it inside spin algebras, spinner. I mean, that's what Clifford algebras are all about. Yeah. So Clifford algebras is a much broader mathematical framework which encompasses all of these kind of things. But yeah. Okay, so maybe what I'll say, I'll sort of cut to the chase for the last few minutes, but is to say something about integrable maps, and then so maybe I'll just introduce the main thing, which is the Kontsevich map. So yeah, Emily was asking about deformation quantization, and Kontsevich got the one of the things he got the Fields Medal for was about deformation quantization. But he has a nice he has lots of preprints which he's never published, and one such is called Noncommutative Identities, and it's about various relations in sort of general associative algebras, and if you like, extending identities in polynomial algebras to non-associative algebras. And then he kind of throws out a rather interesting example. So it just almost like a sort of afterthought at the end of the paper. He has this last section where so anyway, the setup is you have just A now can be any associative algebra, and then okay, the way I mean, you can think of this in a formal way, and then we're going to define a map from a squared to a squared. So this is kind of like a non-commutative plane, if you like, in your algebra. And the particular map that he writes down. Now I'm probably gonna see if I think I can remember it, but so this is the map that he writes down, and he kind of says that this map is integrable in some sense. And then the question is, what does integrable mean? And in a sense, the evidence that he gives is that with a colleague, they did a lot of experiments with a computer, and they took matrices of different dimensions, and then they observed the behavior of orbits of this map, and it seemed to have very kind of regular dynamics, and like the complexity didn't grow too fast and so on. So in some sense, and also maybe for the case when A is just R or C, then actually it's very nice. He makes a comment about it. Okay, so I mean the point is that we were considering this with Joe. Well, in fact, we were considering something slightly more general, but we were considering the case where A is the dual numbers, and now the dual numbers is sort of nice because it's actually still a commutative algebra. So the dual, because you just have this epsilon, but otherwise everything's commutative. So it's kind of easy. So what we did with Joe essentially is we completely solved this map in the case of dual numbers. Like we could write down analytic formulae for the iterates of the map. We could also write down Hankel determinant formulae for the components of the map and so on. So I guess I should explain why we could do that. So with
just a quick question.
Yeah.
I wouldn't expect an arbitrary element associated with algebra to be invertible.
Oh yeah, good point. Yeah, actually that's a great sorry, that's a great comment, Jim, which I neglected to mention, and it was in the back of my mind. Okay, so yeah, great. Yeah, so okay, so there's different ways. Yeah, so okay. So the first thing is that you might want to restrict to, let's say, A star. So if we think of that as meaning the invertible, exactly. Okay, so I mean, in fact, there's an interesting question here. So yeah, some of my collaborators, they prefer to think about this whole thing sort of algebraically and not as a map, from actual elements of the algebra pairs of elements, but more as some kind of ideal in a set of two variables, some relation, if you like, in the polynomials or Laurent polynomial. So there's a sort of generalized notion of Laurent polynomial, which Kontsevich discusses, where you could think of U and V as your generators, and then you also allow U inverse and V inverse. And then Laurent polynomials are just polynomials in those things. So you can think of this as an automorphism of polynomials in these two sort of non-commuting variables. That's one way that you can think about it, and then you avoid the problem about dividing by zero. But even in the case of real numbers, then it's quite important to avoid that. So okay, what I'll say, maybe because I've only got a few minutes, so because I've got lots of pictures to show. So with Joe Harrow, basically we did the case of where A is the dual, let's say D, the dual numbers. And we proved that in a rather technical sense that it really is an integrable system. And the technical sense is that, so the dual numbers is a two-dimensional algebra. And then if we work with the square of that, we have four coordinates. And so what you can actually show is that in the four-dimensional space with those coordinates, there's a Poisson bracket, and then there's two conserved quantities which commute with respect to the Poisson brackets. So that's in the sense of Liouville, that's the strict notion of integrability that we're talking about. So and then let's say now when we come to invertibility, so with let's say with Jinping, so not Wing, with Wang et al, we did we've started doing, at least we've proved some theorems, but the case where, well, let's say we have 2 by 2 matrices, so let's say GL2, so 2 by 2, either real or complex. In fact, there's no harm in making everything complex. Okay, so what I should do, because in theory I'm supposed to stop in 1 minute, so what I'll do is I'll show you some, not lots of numbers, but maybe some pictures. So so what I should say is that this map, when I saw this remarks in Kontsevich's paper, I kind of recognized the map because I knew the commutative version of it, and the commutative version is an example of what's called a Quispel-Roberts-Thompson map. So it's a very nice map belonging to a large family of maps in the plane, which preserve pencils of elliptic curves, or genus 1 curves, actually, of a particular, given in a particular form. So the point is that if you look at sort of nice orbits, compact orbits of this map, so this is just the ordinary map in R2, then you get some nice closed curves, and that compact orbit belongs to, is a connected component of a genus 1 curve in the plane. And so you can, so you can foliate the whole plane by these curves, and then each orbit lives on one such curve. And then there's a parameter which tells you which curve you're on, and that corresponds, in a mechanical analogy, that corresponds to energy. So there's like a fixed energy value at each point in phase space, and then the energy, because it's just a 1 degree of freedom system, the energy tells you exactly which, you fix the level set of energy tells you which orbit you're on. So that's one orbit of this map in the real case. Now, if you extend it to four dimensions with the dual numbers, it's not so easy to plot things in 4 dimensions, but I can plot, I don't know if it's gonna let me rotate it. I can plot different components of the map. And what you find is that there's some nice sort of orbits that go, if you like, kind of tangent to the original, that live, if you like, in the tangent space to the original genus 1 curve. So I think somewhere I've plotted them all on the same picture. And then, then I started trying to plot them in 3D. So you try to at least represent three coordinates at once. So that's like an orbit projected into 3D. And then, but so what you find is that in general, there's somewhere I've done a plot, I don't know if it's where is, which has got all 4 types of orbits plotted together. So you can see, if you like, in the original R2, there's just an orbit, that little black thing right in the middle is that original black curve that I drew. So that's just the sort of original commutative map. And then on top of it, there's this sort of dual part, which is sometimes called the shadow. And the shadow can either be a closed orbit, like this sort of orange curve, which I've also plotted below. This is a shadow which corresponds to a shadow which is tangent in the tangent space to this original curve. But then there's also, in general, transverse components. And so you can think about that in terms of deformations of elliptic curves or moduli space, moving in the moduli space. But so anyway, the map in the Joule numbers is not, it's quite simple in a sense. And then if you add on these θ1 and θ2 and then θ1, θ2 to get all together, you get, okay, I won't show you all the formulae, but you get some sort of more complicated formulae. But yeah, I haven't completely solved the full supersymmetric one. However, what's maybe more nice to look at is if we go to GL2. So this is an orbit. So now again in GL2, you have 4 coordinates and you can choose 4 nice coordinates. And what you see is this looks like the surface of a 2 torus. So actually there are compact orbits which live on a 2-dimensional torus, and so this is again sort of a kind of signature of integrability. And what we expect is that this corresponds to the Jacobian of a genus 2 curve. But yeah, we haven't worked out all the details. But maybe I can show you. I mean, so just to kind of finish, I'll try and show you one thing. So what's rather beautiful in the case of 2x2 matrices is that you can write everything in terms of the trace and the determinant. So you can pick your 2 initial matrices and the trace and the determinant of the 2 initial matrices. Now that's not quite enough. There's one more thing you have to fix. And then you get a nice map in 4 dimensions. And the map so this is what the 4-dimensional map written as 2 second-order recurrences. And that's what you get from taking the trace and the determinant of your 2 initial 2x2 matrices, and of course invertible matrices. Otherwise, you're going to D is determinant and T is trace. So there's a nice kind of algebra there, but actually it's not quite as nice as it could be. And in fact, the best thing is to work with not just the trace of U and the trace of V and their determinants, but also the trace of UV. And then you get a very nice, I mean, you don't have to make any other assumptions, and you get a nice closed form mapping in 5 dimensions. And then the 5-dimensional map, sorry, I'm scrolling through text file. This is the 5-dimensional map, which has a rather sort of elegant form. And then this 5-dimensional map has 3 conserved quantities. And then what Jing Ping managed to do, she's an expert on what's called Poisson double brackets. So when you have an associative algebra in general, a non-commutative algebra, there isn't a sort of easy way to define a Poisson bracket other than just the commutator. So the commutator is not such an interesting Poisson bracket, but there is something called the Poisson double bracket, and then she was able to reduce that down to this 5-dimensional space, and then prove that really this map is completely integrable using some nice Poisson brackets that she calculated. So we know that this system in 5 dimensions that you get from 2x2 matrices is integrable in a technical sense. We don't know exactly how to integrate it yet, but we have various tools that we can apply to it. But also this kind of matches with a prediction in Kontsevich's preprint, which is he said that for n by n matrices, there should be a nice system in dimension n squared plus 1, and that's what we found. But that's where we are at the moment. Yeah, so I think that's a good place to stop. But thanks for listening.